All right, so today we are really lucky to have Yali, who is an assistant professor at King's College London. Her research aims to enable machines to exhibit cooperative and trustworthy behavior in intelligent decision-making tasks. Her work focuses on reinforcement learning and multi-agent cooperation, with interests in topics such as generalization, zero-shot coordination, evaluation of human and AI players, and social agency. For her work in reinforcement learning and cooperation, she was chosen for the AAAI New Faculty Highlights Program, a Rising Star in AI, CAUS 2023. And prior to her current position, she received her PhD from the University of Technology, Sydney, and was a postdoc at the University of College London. I know a lot of folks are really excited about this talk, so let me hand it over. And thanks again for coming.
Yeah, thank you, Eugene, for this very kind introduction. And I'm very pleased to be here today to introduce my recent work with you. So the title of my talk is Reinforcement Learning with Human Values. And so I would start with some very well known the success of reinforcement learning. So for the reinforcement learning, I think so many of you might have have heard about or been involved in the advancement of the reinforcement learning in the recent years, and there are like some enormous success in the solving some very complicated decision-making tasks, like playing the chess, playing the Go, or playing the StarCraft, or playing the complicated multiplayer video games like Dota 5. And also recently in ChatGPT, they also used this. They also started using this reinforcement learning to fine tune their agent for the value alignment. So for the reinforcement learning, it is kind of learning from the interactions and the trial and errors based on its experience. So it learns from its feedback, and it collects data based on based on its interaction with the environment. So this is kind of typical is different from the typical machine learning task where the data set is fixed, that you just learn a mapping to fit the output to fit the output and the input mapping. And so for the reinforcement learning, so basically this is I just want to give a bit background. So this is a typical kind of paradigm. So they are like two important elements in the system. So we have an agent and an environment, or sometimes we call it kind of tasks. So for this agent, it is able to take some actions that would influence the state of the environment. So for the environment, it would undergo some kind of state transitions, and it would emit the next state and a reward signal that provides some kind of immediate response to how good or bad this agent's action is. And this agent, so usually we discuss it by parameterizing its policy by some kind of neural network. So it's a kind of deep reinforcement learning. And so for the reinforcement learning agent, its typical objective is to maximize the long-term return, or maximize the discounted return, so that it would be able to achieve some kind of goals associated to this kind of reward functions. And so in the last few years, I think we have really see many of the success examples. But I would like to point out that the existing success of reinforcement learning often comes with the well-specified reward function. So for example, in this kind of board games like chess or Go, it's clear that if you win the game, you get some positive reward. If you lose the game, you get a negative reward. But we would like to. But the point is that actually the quality of the reward function, it does not come without a price. The quality of the reward function would largely depend on the designer, on the designer's understanding of the task. So if the designer has a good understanding of the task, it might design some kind of reward signals that would easily guide the agent to achieve the goal. Otherwise, the agent might be able to learn to maximize reward, but it's not kind of realizing the goal that's designed, that's in the mind of the designer. And on the other hand, sometimes the reward function might be difficult to specify. So for example, if you would like to try, you would like to train some kind of agent to maximize the satisfaction of some users, if it's kind of a healthcare robot or like a home care robot, you want this agent to maximize the satisfaction of some of the different customers at home. So this would be kind of this would be kind of the scenario that the reward function would be very difficult to specify. And in this case, we want to ask the question, so can we train the reinforcement learning agent without a well-specified reward function? And so here I wanted to mention about the roadmap that's discussed in ChatGPT by OpenAI. So basically, what they have mentioned is that the first stage they do the pre-training based on the first stage they do the pre-training based on the offline data, and then in the second stage they wanted to tune this model to this chatbot to generate conversations that's aligned with human values. And this is kind of something that can be subjective to be, and that can be hard to specify some kind of exact reward signals. So what that's being considered doing here is that so we could ask the chatbot. We could ask a chatbot to generate different conversations, like a different conversation that's denoted kind of as A, B, C, D here. So based on these different options, we could bring the human in the loop. So human could provide their preference over this kind of different comments. So the humans may say that, okay, I would prefer the response A over B. So although it's kind of it's hard for the human to specify reward signal, we don't ask humans to specify some kind of exact reward signals of whether this would be a positive 10 or whether it would be a negative 10. This kind of numerical values, but we just ask asking the human to provide this kind of binary preferences. This would be able to allow us to train a kind of reward model that would fit into the preference of human laborers. And then based on this reward model, so basically they could follow the standard of policy optimization steps to do the training or to do the fine tuning of the chatbot based on this reconstructed reward model. So basically this is a framework for the reinforcement learning from human feedback. And let's look at the difference. Let's look at this how is this different from the typical reinforcement learning algorithm. So for the reinforcement learning algorithm, so usually it receives observation, but also the reward signal from the environment. But in the case of RLHF, so there would be not reward signals directly coming from the environment. So there would be some kind of let's say human laborers that would be able to provide their preference over the behaviors, over the trajectories generated by this R agent, and then we could train the predictor that would be able to align with this with this reward signal with this human preference, and use this reward predictor to train this reward predictor to train the R agent. And so basically here, what we consider is to use this human preference framework to train this to train the robot manipulation tasks. So here it is an example. So basically here we have two trajectories on Majoko biped robot. And based on these two trajectories, we could ask human to provide the preference, and we would see that okay, we would prefer this trajectory as it seems more balanced, and this seems more balanced, and this would kind of based on this preference, we could just recover the reward signal without asking humans to specifically specify that. And the main reference of this of the content content below would be the two papers. One is on the meta reward net, which is published last year, and the other paper is a very recent work, which is we consider how to reuse the labels from some existing task. So for preference-based RL, so far I think we have the most currently the most important message is so far is that so basically if we don't have the rewards, we don't have the reward signal, or if the reward signal is very hard to specify, we could use the human preference to generate. We could use human preference to generate this kind of alternative feedback that could be used to recover the reward signals. But we want to point out that actually there's also another key challenge comes. So the humans labels would also come with some price. So we want to improve the efficiency of the human feedback. So take this as an example. Take this task. This is a door open task. So for this door open task, so basically for the existing baselines, it would require 250 or 500,000 or 250,000 or 500,000 of human labels, which is also very expensive. So we are thinking that whether we are able to reduce this number, where we are able to reduce the number of feedback that we need. So basically, if we reduce the number of feedback, so this would lead to the problem that we have very little data to train the reward, to recover or to train the reward model. And based on this, and if we can't get an accurate reward model that's aligned with the human's kind of binary preference, and then this would lead to another problem that if we want to fit some kind of critic function that is able to evaluate agent actions, and the evaluation of this Q function or state action value would also be inaccurate because it comes from the inaccurate reward functions. And then we are thinking that whether we are able to improve the feedback efficiency in this model. And so what we consider the idea is that so we usually rely on the accurate reward signals, accurate reward predictor to learn the Q function. But we were thinking that whether we are able to learn this Q function, whether we would be able to learn this Q function, to use this Q function to predict the human preference, to align with human preference, so that we just skip one step about using the train the reward function and then train the Q function based on the reward function. And so this is the basic idea. So I will explain about this later. And so here is some kind of some background information of preference-based reinforcement learning. So for preference-based reinforcement learning, here it is it is pretty straightforward. So basically, based on the trajectory, so let's say we have two trajectories, sigma 0. We have two trajectories, sigma 0 and sigma 1. Based on these two trajectories, we compute the probability of sigma 0 is better than sigma 1. And so this I find this summation is actually the reward of different time steps in this across this trajectory. And this is just a Bradley-Terry model, and based on the human's preference label that we have, so it's just binary labels, and we could recover the variables, just recover the reward function by solving this binary classification task. And after we have this reward function, we will be able to learn the policy based on that, and basically we could So basically, we could pre-train this. We could collect data, pre-train this reward model, and then train the policy. Or we could also do the alternative training. So we update the reward function. We update the reward function along with the optimization of the agent policies. And so, as I mentioned, our idea is to try to reduce the confirmation bias that comes from the inaccurate reward function, because we wanted to reduce the number of preference labels, that we need that we need. And so in that case, we have a less accurate reward function and less accurate Q function. So our idea is actually in general summarized in this one slide. So basically, instead of using this sum of reward to indicate the goodness or badness of the trajectory, we have used this Q function. We have to use this Q function to represent the quality of the trajectory. So we use the Q function to represent whether the trajectory sigma 0, trajectory 0 is better than trajectory 1. And so Q theta would be the critical function that we would like to learn. And so based on this reconstructed or this redesigned preference, based on this redesigned preference predictor, we could use this to still perform the standard binary classification, so that we could just update the parameters in these Q functions. So I heard some.
Yeah, a question. Yuta, do you want to ask a question?
Yeah, sure. Hi, I have a question about the preference predictor. So is the predictor self-parameterized at all, or is it only parameterized through the Q function?
The preference predictor, you mean this P function, right?
Yeah. So like is there any like coefficient or parameters to be learned for the P function itself, or is it only through the Q function and just like a deterministic function of the Qs?
Yeah, thank you for this question. Actually, so currently this P theta, the parameters is only from the Q function. So there's no actual parameters associated to this P theta. So basically, it's just a very simple Bradley-Terry model. So we have the Q values of two trajectories, and we want to decide which one is better, and we just use this equation that I show here to generate a soft probability between the 0 and 1 to see whether this trajectory 0 is better or not by the probability provided by this equation.
Okay, thank you.
Okay, great, thank you. And so basically, based on this redesigned preference predictor, and we could kind of use this predict the preference based on the Q function. And so for the Q function update, it still follows the standard Q learning loss. So it also follows the standard Q learning loss. And so basically, as we see that if we update this Q theta, the Q function, it still relies on the immediate reward signal. So this is typical Q learning loss, and the update this Q still relies on the immediate reward signal. So, but basically, as we notice that we are not using this reward signal R hat to predict the preference. Then how could we get the gradient information to update this gradient information to update the parameters in the reward signal function R hat phi? This is so we have come up with this kind of bi-level optimization, bi-level programming objective. So in the inner loop, it is the standard Q learning loss. So we update the standard Q learning loss and assume that we know this. Assume that we just have some fixed parameter alpha I hat phi, we'll be able to update the parameters of Q based on this Q-learning loss. And so in the out loop, here it's just one minor trick that we have used in the out loop. So basically, we want to update the reward function R hat phi based on this preference. Oh, sorry, I think did my screen sharing still work?
Yeah, it's gone black all of a sudden.
Oh, sorry.
No worries. I'll let you know if anything changes.
Okay, let me try. Is that a back?
It is back. Yes.
Okay, great. I think I just randomly click on some other places, just disappears. Okay.
While we have you pause, there is a quick question from Rupali.
Yes.
Yeah. So in like the first equation, so you're using the Q value of, so I'm thinking S0 and A0 are the first state and the first action. So is this like the Q value of the first state and the first action? Are you using it as a proxy to get like the value of the whole trajectory? Like, I'm not sure if this question is clear.
Yes, understood. Yeah, that's a good question. So basically, yes, we just use this. We just use the starting point of the trajectory to and predict Q value. Use this to denote. Use this to label the quality of this trajectory.
Mm-hmm.
And basically, based on for the full trajectory, we could cut that into different pieces, and we could use this different pieces. So for one trajectory, we could use it for multiple times to construct this preference predictor. That we use the starting the starting state and action and the trajectory.
All right, cool. Thank you.
Yes, thanks. And so basically, so as I mentioned, in the inner loop, we still do the standard Q-learning, and in the out loop, as we mentioned, we also need to know the reward predictor R hat phi, and but in this meta loss that we defined here is based on Q function, not R hat. So how could we obtain the gradient? How could we obtain the gradient information of this R hat phi to update it? So here is something that we call the meta gradient here. So basically, in the gradient information of this Q theta, we would have this R hat phi here because the loss function for Q learning would rely on the reward predictor R hat phi here. And if we take the gradient information, the gradient information of theta, this R hat phi would appear in the gradient information of this theta update process, and we could employ the chain rule to obtain the gradient information for this R hat phi. So this is the expression as we express it into this bi-level programming objective, and I can show this.
Before we go to the next slide, I think there's one more question on this previous slide. Manfred, if you want to.
Can you hear me well?
Yes, I can.
All right. Yeah, no, I was wondering, you mentioned that you're using a Bradley-Terry model, and I was wondering if you took any steps to reduce the issues that Bradley model has with like intransitive preferences, or is it something that you didn't take into account? Thanks.
Yes, thank you. I think that's actually a very good question. So the intransitive preferences. So actually, so far we haven't considered the inconsistencies in the trajectory so far. So we assume that the preferences are consistent. And actually, I think I might discuss this. Actually, I might mention this in the limitation of future works of this. So basically, we don't. So we didn't consider preference. We assume that so for this preference label would have come from one, for example, one labeler, or from several labelers that share the same preference. So for the inconsistent preferences, that might come from a scenario that we have multiple human labelers and they have different preference values, or they have different objectives. So that in that case, there might be the inconsistent preference. But so far, it's we haven't discussed this yet. So I think that can be kind of part of directions for future investigation. I hope that clarify your question.
Yep, thanks.
Okay, thank you. And this slide would just elaborate how the optimization works. So how the optimization works. So for the inner loop, it's a standard Q-learning, and we do the gradient descent. And for the outer loop, as we mentioned, we have deliberately designed this bi-level optimization framework so that we could find the gradient. So that we could find the gradient of the r hat phi through this chain rule. So we first have this loss function taking gradient to the Q function parameters theta, and in the theta's gradient information, as we see that in the gradient information of theta, we could see the r hat here, and then we take the gradient of theta over phi, and this would give us the gradient information for r hat phi. So we were able to update this immediate reward function by gradient, and this would be the so far I think this would be the major content of how the methodology, how the algorithms works for this newly designed preference predictor. And here is just a visualization. Here is just a visualization of the whole pipeline after we have just redesigned this preference predictor. So the agent interact with the environment and the trajectories. The trajectories would be labeled by the r hat phi and the q theta, and the q theta would be used for the preference prediction. For the preference prediction, that it would update the r hat phi, and also for the policy evaluation. So to update the policy, which is actually in our case we use the soft text critique, and for the optimization steps, we also provided the convergence analysis based on some assumptions of the property of the loss function and the gradient norm. So basically, the inner loop and the outer loop optimization steps would also all converge to the local minimum. And so this kind of details, I would not discuss these details here, but this could be found in the main paper. And the next, I would like to discuss some of the experiment results. So we have performed the experiments on the module tasks demand control suite, and also the several tasks from MetaWord. So these are like control the robot to use the hammer to open the door or press the button. And so here are here are the learning curves for the MetaWord benchmarks. So we have several. So we have this 6 tasks here, and this blue line is a soft act critique that is using the ground truth rule signal. So basically, it is performing the best because they are using the ground truth rule signal, and so this purple line is for our algorithm. So basically, we find that in generated it displays faster convergence, like a better sample efficiency, and it converges to the better success rate with fewer feedback, with fewer preference labels. So here in our case, we have used for example, for this open task, we have used 1,000 preference labels, which comparing to the earlier works, they have used they need to use 250 or 500,000 tasks to achieve a good performance. And here are also similar for the results on the module control tasks. And so basically we are just showing the kind of similar results with which achieves higher return with our algorithm. And here I see, hope that it works. So here are like some demos that's generated by the agent trained by Meta Reward Net, which see that so we are able to train this agent to perform some meaningful tasks on this kind of benchmarks that we considered. And so I think that'll be everything for this book. And next I would like to introduce another recent work that can discuss how to reuse labels. So before I move the ears, maybe I just have a check whether there are questions.
Yeah, I'm curious about the optimization procedure that's happening here. Would there be any value in like trying to use some kind of like possibly like differentiable layers, making the full, is the system not end-to-end differentiable?
Yes, I think what you mentioned is what you're mentioning might be exactly what we are doing here. So it's kind of a differentiable layer. So it's end-to-end. So basically we have it's kind of the chain rules. We take gradient to theta and theta takes gradient to the reward function R5.
Oh, okay, got it.
Yeah.
Cool.
I guess you mentioned this actually exactly what we are doing in the paper.
Okay, yeah, I took me a second to get it. My bad. Thank you.
Yes, thank you for the question. So, so now I would like to just briefly introduce another recent work that discuss how could we reuse the preference labels from other tasks. So imagine that based on the previous tasks, we have collected the preference labels for different tasks. For example, for this kind of task as the push the button. So whether we are able to reuse these preference labels in another new tasks that we don't have that we don't have any preference label information on the task at all. So this is we answer this question with like a positively. So we think that so we just prove that it is possible. So we are able to reuse, for example, reuse the preference labels collected for this source task to train an agent to complete the task, to complete a targeted task without any new labels introduced. So this is any new label introduced for the new task. And so the idea for this this work is that we introduce some kind of the optimal transport, the GW alignment metric, so that in the source task we have many trajectory pairs x and x prime, and we want in the target task we also have many other we can select many pairs like y and y prime. We want to align the distance between the source pairs and the target pairs. So basically based on this GW alignment trick, we are able to identify this kind of optimal transport metrics that identify the correspondence between the trajectories in the target task, and the trajectories in the source task. And then based on the preference labels that we have in the source task, so we would be able to compute the preference labels in the target task. So in the target task. So here this matrix is actually a binary matrix indicating that okay, y2 is better than y1, y3 is better than y1. So with this kind of yellow box, and here is here is just the page that I mentioned that the demo is not quite working. So I might try to share another page of demos about that. Okay, so try to share that. And this is okay, you could see that. So this is just the demo. This is just the demo that I wanted to show. So basically, here in the first row, these are the trajectories. These are the trajectories from the source task, which is for the task of button press. And in the second row, these are trajectories. The trajectories in the target task where we don't have any preference labels here. And so basically here, so we have x1, x2, x3, x4 for trajectories, and also for trajectories for target task. And based on this, and based on the kind of procedure mentioned, so we are able to solving the optimal transport matrix and identify the correspondence between the trajectories between the trajectories in source task and a target task. And then this preference label suggests we're able to transfer this information to the target task. So we have the transferred preference label here. So based on the preference label, we could see that. So this, for example, this y2 trajectories, y2, y3, y4 would be better than y1, and trajectory y3, y4 would be the better than trajectory y2, which I think so basically it seems like looks like plausible here. And yes, and this is just the demo for this. And okay. And and then this would be almost the end of the talk. And in summary, in this talk we have discussed that human preference can be the alternatives to traditional reward signals in the scenarios where the reward signals can be hard to specify or just be unavailable. And they also show that the preference information can be effectively transferred to the target tasks to reduce the cost of labeling for new tasks. And so some of for the limitations of this works, as I think one thing that has been mentioned in the questions is that so currently we don't consider the inconsistent preference yet. So basically, if we have multiple humans to generate these labels, it is very kind of possible. It is possible that there might be conflicts among the different humans' preference, and also another thing that currently for the trajectory, the preference is provided on the trajectory level. So we ask human to see that okay, you prefer this trajectory A over trajectory B, but for the good trajectory, it might have some bad actions, and for the better trajectories, it might also include some good trajectories. So this is also kind of not considered yet, and also for the last work that I mentioned about the preference transfer. So currently it works well for this. It works well based and it relies on the similarity of the tasks. So the source task and target task should not be too different from each other. They need to be somehow share some kind of similarity, so that this preference level transfer would work well. And so at the last, it's just some kind of overview of the work in our group. So we have so we work on the many multi-agent learning problems, improving the cooperation, doing credit assignment or communication, and we also work on the evaluation. So evaluation of the agent in the multi-agent scenario. So whether how is the agent performance in competing with others, or how the agent's performance or capacity of cooperation with other agents. And so the work that I introduced is just our recent work on improving the agents, on aligning the agent's values with humans from this human preference based learning framework. And that would be everything for my talk. Thank you for your time, and happy to take your questions if there are more questions.
Yeah, thank you so much for the talk. It was a great talk. I guess I'm going to open the floor to questions. And if we run out of that, I guess we have some extra time to just have an open-ended discussion about preference learning and RL from preferences. So I'm excited that we have some extra time to chat, actually. Cool. So let me open the floor to questions, and thanks again for the great talk.
Yeah, thank you, Eugene.
Yeah, Rupali.
Yeah. So I had a question in just the later part of the talk in terms of when we were doing the transfer of the preferences. So I understand that we're trying to map the distance, right? The Wasserstein distance. Intuitively, I didn't quite understand how do we do that, like with the trajectory or something.
Mm-hmm. Yes, actually, I just didn't introduce lots of details here. So the basic idea is that we wanted to use we use this GW metric based on the trajectory, the data that we have, and then we could learn this kind of transport matrix. The transport matrix that actually identify how similar one trajectory in target task is to that trajectory is in source task. So basically, we can see. So basically, we compute the similarity between the trajectories in source task and target task, and then so when we compute the preference over two trajectories in target task, we're able to aggregate the preference information that we have in source task to predict that. And yes, I guess maybe yes. So it's just about the general idea. So yes, for the more information might be is happy to answer that if you
Yeah, I think I should check out the paper. That would bring more clarity. Yeah, thank you.
yeah, thanks.
Saw someone else raise their hand and then brought it back down, so I no longer know who it was. But yeah, Manfred.
I have the same question about how do you apply optimal transfer, because I think it's really interesting. Which of the papers is specifically, because I couldn't find the
Yes.
plot that you showed that you went through the matching between the X and the Y. I couldn't find an official page of the meta reward net, so I was wondering where can we have access to that?
Oh yes. So the paper I think it's just a pretty recent one. We just put that on the online, so you could find that through this I think ID here. I mean, I can share this slide with you, so could if it helps.
Wonderful, thank you.
Okay, cool. I have a quick question. So I actually have a question about kind of benchmarking about these kind of preference tasks. If you go back and you take some kind of task where you know the underlying preference model, like a synthetic task, and you possibly even know what are undesirable actions or desirable actions, do these methods correctly recover ground truth synthetic preferences?
Mm-hmm.
Is that how these methods are benchmarked? I know correspondingly way less about preference learning than perhaps I should.
Yeah. So for the benchmarking part, actually this the result is also is still evaluated based on the success rate for this kind of meta-word task, or based on the episodic return that's computed from the ground truth reward. So basically, we use the preference information. We use the preference information to recover a reward predictor, and we train the RL agent based on this recovered reward predictor, and then we evaluated it based on the ground truth reward signal from the environment.
Mm-hmm. But so there's never a middle step where you just check, like, does my preference predictor, like, I mean, kind of, I feel like even without the policy step, right? You can just check if how close your preference predictor ranks ground truth functions. And I'm just curious if this is ever done, or if this is not like a standard.
Yes, thank you. I think we have this. I remember we have this result in the appendix, but I didn't put it. I didn't include it in the slides. But I remember we provide some of this results in the appendix, which I didn't really remember that.
I'll definitely go check it out. That's on me for not taking a look at that. And then kind of a follow-up question is, like, how do these methods compare with like IRL type approaches, where you're just actually trying to recover the ground truth reward function, directly?
Sorry, say that again. You mean the inverse RL?
Yeah.
Yeah. Actually, this is a very, very good question. So for the inverse RL, so basically, I think it's also many people might kind of confuse this RL from preference or inverse RL. So the key difference is that so for the inverse reinforcement learning, it would require the expert to demonstrate the behaviors, so that we could recover the reward function that would characterize why the experts demonstrated these behaviors. But for the preference-based RL, so we don't need the expert to demonstrate these behaviors. They would just need to provide very simple binary feedback, say that, okay, I prefer A over B. It's just the binary feedback. It's much easier to be collected instead of asking the experts to indeed do the task and demonstrate the behaviors. I think basically it's I would say that basically they would just be basically, I think this kind of two-line approaches are sharing the similar spirit, that they want to recover the human experts object or human experts goal, but the format, the format or the format of information is different. Yeah.
Okay.
Yeah,
no, totally answers my question. That's, I mean, not having an expert and being able to do online queries is valuable. Totally makes sense. Tom.
Thanks, Sujin. Yeah, I actually had a follow-up in response to that, so that is clarifying. But I'm curious, since I understand that, so in the context of like cooperative AI as a kind of research agenda, or even as a institutional, I guess, agenda, that if you interpret your work as part of that wider project of building cooperative agents, I'm curious to hear more about what you see as the stakes of that distinction between IRL and this kind of preference-based learning, since it seems to me that the degree to which you're leaning on expert feedback or not is consequential in terms of what it means for an AI to be cooperative, or what it's being cooperative with. If you have any thoughts on that, I'm curious to hear, maybe as a way to wrap up this discussion.
Yeah, thanks. So obviously that basically RLHF, it could be treated as some kind of simple model for human AI cooperation. So we wanted to train this. So we wanted to train one agent, a robot or AI agent that is aligned with human preference. And so for this human preference, actually there are like many other interesting questions come up with this. Is that so for humans is basically we are asking these humans to vote an agent that could represent their preference by represent their values by indicating their preference. So basically, we have if we have multiple different humans, so basically this would involve many other challenges that might come from. So for example, relevant to the voting theory about whether the results could be manipulated by some of human labelers, or whether it could just be maliciously, or whether the AI agent could just be maliciously misled by some kind of labelers to some kind of maliciously designed directions.
Yeah, I think there's an interesting related idea in there about, just like a malicious labeler injecting like a utility monster of a labeler injecting some kind of strange preferences into the model by being very aggressive. Yu-Chen.
Hi, Yali. Thank you very much for the excellent talk. I think I have maybe more open-end questions. So I think like the preference-based framework is certainly a very powerful and a very promising framework. And it seems so far for RLHF, this kind of preference-based framework is the most popular way. I was wondering from your perspective for future work, do you think this learning from human preference would be the most promising direction that we should continue explore, or you think there could be any other possibilities for better leveraging human feedback?
Mm-hmm. Yeah, thanks, Yuchen, for the question. Actually, it's a very kind of difficult question. So I see that basically it would be directly relevant to what kind of human information that we have. So to what kind of human information that we have. So basically, I think so. So as we have discussed, so inverse RL, so like leveraging the information of human expert trajectories, or leveraging the preference labels, or maybe ask the humans to provide some kind of natural language guidance to state some kind of comment on the agent action, whether it is safe or unsafe. This kind of natural language description of the tasks. So this would, I think, this would all be kind of very relevant and very promising direction to discuss. And I just noticed that there are like some recent works considering aligning robots with humans, like language command in terms of improving either safety or the performance on the task. So I see that this would also be like just a different format of the human's feedback, and how could we use this information in a better way based on the format or type of information.
I see. Thank you.
So we've reached 10 o'clock. I'm going to stop the recording here.